Here we go with an introduction to PLCs. Since ladder logic is the most common program method for PLCs, we're going to look at ladder logic basics. Ladder logic is a way of representing an electrical circuit in a computer program. Here's a circuit where we have a switch, and we'll call these inputs, and a motor, which is going to be like an output for our program or our PLC. And to see how this relates to a ladder logic program, let's rearrange this. So now we just move things around. We still have the same voltage source, switch, and motor. And if we rearrange it further, it looks like this. We've got the high voltage on one side and a low voltage on the other. So you can see that whenever the switch is closed, current will flow through the motor, and the motor will be powered on. These switches and motors in ladder logic programs are represented with inputs and outputs, are called inputs and outputs. And then the rails are the high and low voltage. And oftentimes the low voltage rail, or the rail on the right, is not shown. But it's always high voltage would be on the left and low on the right, so our convention for current would go from left to right. Again, this is the circuit this is a circuit corresponding to this ladder logic rung. For this circuit, there will be two rungs because we have these two current paths. And let's look at that example. So here's the top rung would be for this circuit, and then the bottom rung is for this output, this light. And the way we're going to show if a rung has current or is evaluated to true would be if it's highlighted in green. So now we've got this switch closed, which in the convention current that we've been talking about would mean the current flows through the motor, and so we'll show that in green. And this switch is still open, so no current flows through there. But let me spend a minute talking about how the PLC operates as far as inputs and outputs are concerned. Before the program is evaluated, before each rung is examined rung by rung, all the input values are stored. So and when I say stored, I mean the physical inputs are mapped to bits in memory. And if that input was at high voltage, or if that input terminal was at high voltage, meaning the connection was made to high voltage, then that bit in memory is set to 1. And if the input terminal was open or at low voltage, then that bit in memory is set to 0. So all those are scanned and set in memory, and then the program is evaluated. And so these are just instructions to look at bits in memory. These have nothing to do, well, as far as the processor is concerned, these don't have anything to do with physical inputs and outputs. They're just bits in memory. So this bit in memory is evaluated, and if it's 1, and so that's true. And then this bit, outputs have the same thing. They're, as far as the processor is concerned, just bits in memory. So there is a bit in output memory that corresponds to this motor. And so that bit is set to 1. And then this rung is analyzed. So this bit in memory was 0. And so the bit in output memory corresponding to this output is set to 0. And after all the rungs are evaluated, then the mapping is made from output memory bits to physical outputs. So again, we scan all the inputs, assign those values to input memory bits, execute the ladder logic program. Then once that's done, well, during that we'll set output memory bits, or assign values to output memory bits. And then once that's done, the output memory bits are mapped to the physical outputs. I just wanted to get that out of the way so that you're not thinking the whole time that whenever a rung on a ladder logic program is true, that the output is immediately turned on. We can still think of these instructions as pertaining to the physical input, so we could call them examine if opened or closed. For example, with this circuit that we looked at, if it's open, the motor is going to be off, and it's closed, the motor is going to be on. So this is a symbol for an instruction called examine if closed. And it's going to be true if it's closed and false if it's open. So examine if closed will be true if it's closed, which means that this output bit gets set to 1. So this is open. And here's another circuit where the motor will run as long as the switch is open, and then it will stop when the switch is closed. So in this case, we want our ladder logic program to set the output memory bit to 1 if the switch is open. So we're going to use an examine if open instruction. So that's what this looks like, and that would be evaluated as true, and so the motor output bit gets set to 1. So again, on the whole cycle, the inputs are evaluated and assigned to the input memory bits. So this one is a 0, and you can also think of this, instead of examining the physical circuit, you could just call this a not in Boolean algebra. So not this input bit would evaluate to true because it was a 0, and so then this output bit gets set to 1. Now, since we're talking about memory bits, we need to discuss how they are referred to. So here we have inputs A and B and outputs X and Y. Well, again, these are specific bits in memory. So one convention is to have the letter corresponding to if it's an input memory bit or output memory. So I for input, O for output. And then the number after that would be the byte number in memory, and then the number after that would be the bit out of that byte. So each byte has 8 bits. So you could have 8 switches connected to, or wired to these terminals. So 8 switches would be mapped to 1 byte, could be mapped to 1 byte. Anyway, here there are different conventions for different manufacturers of PLCs. Siemens uses this convention. I is for input, but Q is for output. And there's a % sign preceding it, and then you have the byte number and the dot separating it from the bit number. So this right here, this switch is input memory byte 0 bit 1, and it corresponds to the first or terminal 1 on an input module, but we'll get into that a little later. And this would be terminal 0 or bit 0. And then this is output memory byte 8 bit 3, and that corresponds to some physical output. And here's output byte 1 bit 2. Now, talking about input modules, here's a little drawing of an input module, and it has 8 terminals, and each one of those is mapped to a bit in memory. So you can see that when the inputs are scanned, this terminal was high voltage and this was low voltage, and so this bit in input memory is assigned to 1 and this bit is assigned to 0. Let's see the program that goes with this. So we have this bit and not bit 4, and then that is assigned, the result of that is assigned to output byte 8 bit 3. So examine if closed on switch 1, examine if opened on switch 4, and since these two are in series, current has to go through both of them in order to power output 8.3. So there are 2 different ways of looking at it. You can either look at it as bits in memory, or you can look at it as a physical circuit. So examine if this switch is closed, examine if this is open, and then power this output. So current has to go from the high rail to the low rail. Or we could treat this as just the bit and then not that bit, and since these are in series, that would be a Boolean and then the result of that Boolean operation is assigned to output byte 8 bit 3. And here we have not input 1 and input 4, so that would be not 1 and 0, so 0 and 0, and so we're going to assign a 0 to output byte 1 bit 0. And instead of switches, we can also have push buttons, so normally open and normally closed, and it's just important to keep track of the terminology, or maybe not terminology, but the way you're describing what happens, because when you press a button, if you have a normally open push button, that's going to have a different effect than pressing a button on a normally closed push button. So normally open means the The switch is open when you don't press it, and normally open is closed when you do press it. So when you're not pressing a normally open, examine if open is going to give you true. When you're pressing a normally open, examine if close is going to give you a true, or a 1. Now a normally closed button or push button is the opposite. When you're not pressing it, examine if close will give you a true. When you do press it, examine if open will give you a true value, or evaluate to true. Or you can look at the bits in memory. So whenever all the inputs are scanned, this is open, so you'll have a 0 there, and so not that bit gives you true. And when you press it, you have a high voltage, so a 1 is assigned to that bit in memory. So here's that bit and evaluates to true. So it's just kind of not intuitive, because you could have a start button and a stop button, and you might have the start button be normally open and the stop button be normally closed, and whenever you press the start button, the motor starts, or when you press the stop button, the motor stops. And so even though they're normally open and normally closed, you'd have to have an examine if closed and examine if open. And we'll look at that in a second, because I know a visual will help more than words. This shows the mapping of the output memory to the physical output. So here we have a complete system with input terminals and output terminals. So we've got these, the input is scanned, and both those bits in input memory are assigned 1. Then our program is evaluated, so we have 1 and 1. So a 1 is assigned to byte or bit 1 of byte 2 in the output memory. And then after our program is done executing, then that 1 is going to be mapped to high voltage at this output, the physical output. So instead of thinking of electrical current and switches being open and closed, you could think of the ladder logic program as Boolean operations. So examine if open would be not. So here we have y is not a, so not a gives you y. So if a is 1, then y is 0. If a is 0, then y is 1. Here we have an and sometimes it's easier to think of it in current. So in order for current to reach y, then both a and b have to be closed. So these are examine if closed. So if a is closed, or if that bit in memory is 1, then that'll evaluate to true. And if this bit in memory is 1, that means this switch is closed also, so that will evaluate to true. So true and true gives you true for y. Or if they're both closed, then you have current going through. And parallel switches in parallel would be an or. So if this is true, then then y is going to evaluate to true. Or if this is true, then this junction here will evaluate to true. And you can think of it as current. If this button's pressed, then current could take this path. Or if this button's pressed, then current could take this path. Or if you have both buttons pressed, then current will still reach the output. But in series, that's a logical and in parallel, that would be a logical or for inputs. And then there are different combinations of these. So you have NAND, where the output is going to be true in every case unless both of these is true. A NOR, where the output is going to be, if either of these is true, then the output is going to be false. And exclusive OR, where the output is true only if one or the other is true, inputs is true. So here's an example to wrap up the video. I'll try to step through this quickly. Remember that the inputs are scanned, they're assigned to input memory, the program is executed, and the results are assigned to the output memory. And then the outputs are actually turned off or on, depending on the memory. So here we have our system where we have 1, 0, 0 for our inputs, because this button is normally open, this is normally closed, and this is a normally closed relay detecting an overload. Since there's no overload, then it's closed. So 1, 0, 0. And now we can evaluate our programs. So we've got stop, that's a 1, so that's true. and this is 0, and the motor bit, so this is an output bit associated with the motor. And we'll say that last time the program ran, the motor was off, so this bit was 0. Or really, this bit was 0, so the motor was off. Anyway, so this was 0 from last time. So now we have 0 or 0, and that's going to be false. So we have true and false, and so this rung is going to evaluate to false. So the motor's off. And here's that. I said the motor's off, but really this bit is assigned to 0. So here we have not that bit, and that's going to be true, and so then this output bit for the green light is going to be set to 1. And then here we have the motor bit that's 0, and so this is false, and the red light output bit is set to 0. Now we press the button, and so we have 1 1 1 on our input, and we'll go redo the program. So here we have 1, or this is true and true and true. So after that gets evaluated, we can write a 1 to this bit, and now that's 1, so that gets, or anyway, that's 1. And then we'll see how the execution goes. It would move to the next rung. So these get evaluated. Now we have not the motor bit, so since it's now 1, this is going to be false, and this bit gets a 0 written to it. And now the motor bit is 1, so this is true, and this output gets a 1 written to it. And so after we've evaluated this, then the outputs get mapped, output memory gets mapped to the physical output, so the motor would turn on, the green light would turn off, and the red light would turn on. Okay, we let go of the start button, scan the inputs, now we have 0 1 1. But last time, whenever we evaluated the program, the motor bit was set to 1, and so that's still 1. So we have, this is true, this OR is going to evaluate to true because one of them is true, so we have true, 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 so the motor bit stays 1 and nothing changes even though we let go of it, so this is latching on the motor. Now if we press the stop button, we have 0 0 1 on our input bits, and so we'll evaluate the program with those values. So now we've got 0 here, so that evaluates to false, and since this is in series, then that would, no current would go through, or in other words, this is ANDed, so it's going to all evaluate to false. And so we would assign a 0 to this motor bit, and then we go to the next rung. Now we have a 0 here, and that's knotted, so that becomes true. Assign a 1 to the green light bit, and the red light bit gets a 0 assigned to it. And after those are assigned, we finished evaluating our program. Then the memory, output memory, is mapped to the physical memory. Okay, so now let's see what happens when we let go of the stop button and the inputs are scanned again. So now we're back to where we started, where we have 0 1 1, and the motor was off last time. So this is that situation. One more case to look at: what happens whenever the overload relay is tripped. Say we start the motor, so everything gets started, we let go of the start button, and the motor's still going, and then we have an overload. So that means that this is open. So whenever we scan the input again, we'll have 0 1 0, and since that overload is ANDed with the others, then the motor output bit is going to have a 0 written to it. And so we're back to the motor. Okay, so this bit is 0, so green light output bit gets a 1 written to it, motor bit 0, so the red light bit gets a 0 written to it. And then the output memory is mapped to the outputs, so we'll have off, on, off. The last thing to look at is the scan cycle. Here's what happens when a PLC is turned on. We go through these startup processes, and then we reach the scan cycle. So as long as the PLC is in run mode, it's going to be repeatedly doing this. So it does this section once, and then it does this over and over. And I've been talking about this, but just to review what happens. First, it writes the output memory to the outputs. So it maps the output memory to the physical outputs. And then it copies the state of the physical inputs to the input memory. So it maps the inputs to that memory. Then it executes the program cycle. And OB means organizational blocks. So it's a way of modularizing code. And so we evaluate the instruction, and in this section, in part 3, we're only manipulating bits in memory. And then, excuse me, self-diagnostics are performed. And so during this whole cycle, if there are any interrupts or communications, then they'll get handled immediately, and then execution will return back to these steps. So we have map the output, scan the input and map it to input memory, evaluate the program, so that will change memory values, and then go back and update the physical outputs with those new memory values, and update the input memory values with the physical voltages or currents, if you have a current input module, at the memory or at the physical input.